So we're back to the methods of variation parameters. So nothing's really changed. The only difference now is going to be to the nth um, derivative. That's where we're going to. So we talked about when it's equal to 0. So now our situation is, well, what if it's given, equals to a function in terms of x? Okay. So in general, we're going to have our particular solution to be given like this, where again, when we had just y prime, you only had v1 and v2, but now this is the nth derivative. We have nth different v1s and all the way to vn's, right? With its respective y1 and ynth degree portions. Okay, so we're just bumping it up all, to the nth degree itself. Everything is exactly the same, even how we do it. It just gets a little bit harder as we go along. Okay, so for example, this was the general variation parameters of just degree 2, right? So it's just a second degree. But now if I want to nth degree, now we have a bit of a situation. It follows the same template where we have the same, same pattern here. That goes all the way to the y sub n. But we also go down to the nth minus 1 degree of derivatives. So this process just gives you all the derivatives of the y function. And these are all constant, right? These are all going to be the same going down, just like these are here. Okay. So the only thing that really changes is the actual derivative of these y values, or y1 values. And remember, these y1 values are the general solution, right? And these will always give you a nice, beautiful linear combination of it. Okay. So then the question becomes, how do we solve for these type of situations? Okay. So for that, we're going to be using something called Cramer's rule. So Cramer's rule is very popular in algebra, and especially in linear algebra. It's a way to solve for a system of equations a little faster using matrices. Okay? And that's exactly what we're going to be doing, is now we're going to put this in a matrix to make it easier to simplify and find the answer to this. Okay? So the first off is we're going to find the matrix of derivatives, meaning it's all the y1s with their respective derivative going down the column. So then y1 and its respective derivatives are the first one, y2, so forth, until we get to nth value itself. Okay, so this process is called the Dworskian, and we'll talk about that much more in detail later on. But as of now, we do a nice brief introduction of how this is actually applied. But let's go back to Cramer's rule. So how Cramer's rule applied is, well, when it came to just solving for x and y, it's the derivative of dx times the actual, sorry, not derivative, the determinant of dx over the determinant of d, which is going to be this portion. This is going to be our actual d matrix. And then y is the determinant of dy over the determinant of d as well. And we'll talk about how to get those dy's. They're pretty simple itself. But for now, what we're going to deal with is how do we get the actual determinant of this d value. Now, the determinant of this matrix here is actually called the Dworskian, okay, or denoted as this for short. Okay. Now, the question is, how do we find this Dworskian portion? Because it's a little different going off the bat. Because remember, when it comes to finding the determinant of a 2 by 2 is just, for example, it just cross multiply. This times this minus that times that. But once we get to higher, right, 3, we have to simply break it down. So when it comes to that, we're going to find something called, again, back to linear algebra, something called the cofactors of the Dworskian. And that's going to tell me it's going to be a plus or minus, because again, when we do the determinants of a 3 by 3, for example, the first part is a positive, then we have a matrix, then we have a negative, then the matrix, then a positive, and it follows that same template, plus, minus, plus, minus, plus, minus. So the question is, well, according to each individual case, is it going to be positive or negative? That's this part over here. Okay, so that's going to tell me if each individual part we're looking at is going to be a positive or a negative in front of it. And then we take the determinant of that itself. Okay, that's going to be this top number there. Okay, because again, this is only two variables we're dealing with, and variables itself. Okay. Now again, that's just finding one thing, right? They're just finding each individual ones and solving for those in each individual ones, right? So these are the individual y1s and y2s and so forth. We still have to solve for the v's, so the v1 and the v2s and all that fun stuff eventually, the vn's itself as well. So to do so again, we go back to, and this is the same thing as what we did earlier for the variation parameters. But again, now we're just doing the nth degree, where the bottom is the entire Dworskian of this. So this is the determinant of this portion. And the top is the individual Dworskian here. So again, it's the same type of process. We're dividing, but because of it, we're doing the variation parameters, we multiply by the g of x, which is going to be the last one here, and then we just take the integral, right? So this process is the same as the variation parameters we did earlier. We're just separating because now we're just having the nth degree derivative. Okay. So the question is, how does this all put into an actual question, right? How is this applied into actual problems? So let's actually try this out. So find the general solution to the Cauchy-Euler equation with the given solution. So we already given these are the fundamental solution set. Okay, so knowing that fact, we can find the Dworskian right off the bat. Okay, but before we do so, I'm going to simplify this equation. I'm going to make it look a little nicer. Okay, so I just want y triple prime to begin with. So I'm just going to divide this entire equation by x to the third. So when I do that now, I now get this. Now if you're wondering, well, why would I do that? Is, well, in the end, I have to integrate. And I really don't want to integrate this, even though it may simplify this, because now my g of x function is just going to be sine of x, which is actually a lot easier to deal with instead of in the x to the third here. I really don't want to think about trying to do some integration by parts if it so happened to, because I'm not sure if it would actually cancel any x's at all. But this way, at least has something to deal with. Okay. All right, so we have one of them. That's our g of x for each individual vk. Okay, now we got to figure out the Dworskins of each individual case. Okay, so first off, we're going to make our actual Dworskian matrix using our derivatives of our fundamental set. So first thing is, the first row is going to be the actual fundamental set, so x to the negative 1, and x squared. And we're just going to take the derivative twice according to our rules. That's why it's n minus 1, so we have 3, so 3 minus 1 is 2. So this is, derivative is 1, derivative of that's going to be 0, derivative of this is negative x to the negative 2 power, derivative again gives you positive 2x to the negative 3 power. Okay. All right, same thing here, 2x, 2. All right, so now we get the determinant. It's a 3 by 3 matrix, and I kind of hinted here. All right, so this is where knowing linear algebra comes into play. You're actually ahead of the game. So it's going to be positive x with the matrix of negative x to the negative 2, 2x to the negative 3, 2x, and 2. Minus next one on the row. So it's going to be 1, 0, 2x, and then 2. And then plus the last one is this matrix. And there we go. So now, so it's a 2 by 2 matrix, so this times this minus that times that, multiply it, same process as we go along, and eventually we get negative 6 to the negative 1 power. So this is going to be considered our Dworskian. So at the bottom of all of these is this. So we'll leave it as that, as kind of like notation purposes. So now the next step is to find each of these. So we have this, we have that, we need to find each of these. And these are the k values, right? So we'll just start from here. Now, like I said, there was an easier way of doing this instead of figuring out what's going on here, right? And this is usually how it's going to work. And it's going to work for, let's say, for our class itself. Okay. So to find W1, like in that process, so I'm just going to plug in. So n in this case is going to be 3. Okay. So we know n is equal to 3. And then we're just going to subtract. So it'll be negative 1 to the 3 minus 1 power. So that's how we do that part. And now, again, this is a matrix. Okay. Now, the best thing is this new matrix here is actually not a 3 by 3, but a 2 by 2. It drops 1 degree down. So how it's going to work is whenever you have a 3 by 3, and this actually works for a 4 by 4, but we'll just always going to do 3 by 3s. For the 3 by 3 matrices, we're always going to just delete this entire bottom row. Okay. Now, if I just delete this entire bottom row, now we're left with these 6 numbers, or 6 entries, right? Now, this 1 here says I'm going to eliminate the first column as well. So I'm just going to go like this, and then like this. And what's left over gives me a matrix of just a 2 by 2. So it drops 1 degree in both dimensions. Okay. And then from here, we just find the determinant. So multiply each other minus these portions, and then we multiply by 1 squared, which is just going to be positive 1. So this ends up giving us just 3. Okay. So now let's try the Dvorsky with k equaling 2. So it'd be negative 1 to the 3 minus 2 power. Okay. Now again, we're still eliminating the entire bottom row, but this time we eliminate the second column because the 2 is 2. Okay. So if I eliminate the second column, now is left over is x1, x squared, and 2x. Just like that. Again, same process. We multiply minus this, and we multiply by, in this case, negative 1, and we end up with negative x squared. All right, we just do it one more time for W3. So now this time, it's going to be third row and third column. There we go. So this is negative 1 to the 0 power, so it's going to be 1. So that times that minus that times that. So again, this ends up giving us negative 2x and negative 1 power after we simplify. Now finally, we have everything we need to solve for this kind of situations. Okay, so to solve for VKs is going to be the integral of sine x times each individual Dvorskian divided by the actual Dvorskian. So divided by this value here. Okay, and at the very end, we're just going to multiply by each yk. Right, so we'll just do each one individually. So we'll do V1 first. Okay. So V1 is going to be the integral of sine x times the Dvorsky of 1, which is a nice just 3, all over the entire Dvorsky. Just like that. Which is great because this actually ends up simplifying just to negative 1 half integral of just sine x, which is really nice to do, right? Oh, actually, and then bring this up there, which is not so fun. This is integration by parts. Okay. So let me just rewrite the other ones. as I go along. So again, sine of x over negative 6x and negative 1. And now I use this one, times negative x squared. So simplifying this again a little nicer. These negatives cancel, so you just get 1/6 integral of x to the third sine x. And then finally the last one. And this one's going to be times negative 2x and negative 1 power. So these are nice. They actually x's do cancel, which is nice. Negatives get away. So we get now 1/3, and we'll just sine x. So these two, you have to do integration by parts for. The good thing is there's only one here. This is going to have to do a couple breakdowns of it. Okay, but eventually, when we end up getting is finally our general solution. So when it comes to our general solution, we use first our fundamental set. So it'll be C1 times x plus C2 or C2 x to the negative 1 power plus C3 x squared, right? So that comes from our fundamental set. That's our general equation. And then plus all of these. So remember, it's each one of these, the answer to these, times each individual values. Okay? So eventually, after some simplification, we get this. As our final answer. Right, so this is times y1 times y2 and times y3. So after you do these integrals, this will be multiplied by x, this will be multiplied by x and negative 1, and this will be multiplied by x squared. And eventually, kind of nicely, it simplifies to that. Lots of algebra. So let's try another example. So find the general solution to the Cauchy-Euler equation. So this time we're not given a fundamental set, so we actually have to find one. Okay? So to find our fundamental set, we just find solve for the homogeneous part. So this is going to be r to the third plus r equals 0 for our characteristic equation. So we're going to get r equals to 0, and r is equal to plus or minus I, because it's going to be imaginary numbers, right? You just subtract the 1 over. Okay. So in that case, so our first equation is going to be e to the 0 x, so just 1. And then the next two are going to be cosine and sine because it's imaginary. So again, r is 0 in this case. Yes, it's 0. So we're just going to have cosine x and sine x. Okay. Again, if you're wondering, right, technically this is r equals 0 plus or minus I. That's where the 0 comes in. So these are all e to the 0x times this, e to the 0x, because this is our b. So there. You guys are just wondering where that is. So this is our fundamental set. So now we can find the Wurskian using this process. So Wurskian is going to be 1 cosine sine, and with the respective derivatives. So this is nice because this is going to be 0, 0, and these just alternate sine and cosine with the negative in the fronts. And again, now we just find the determinant of it. So using the same process. And this is really nice because the zeros actually a lot of stuff cancels. And this ends up simplifying to just sine squared x plus cosine squared x, which is even better because it just equals to 1. So our Dvorsky is just 1. Just like last time, this is 3, so we know n is going to be 3. So when now we find our Dvorskys 1, 2, and 3, it's going to be negative 1 to 3 minus 1 power, and it's the same process. Let's break it down to 2 by 2. We're just going to get rid of the third row and each respective k. So get rid of this one, and we're left with cosine x, negative sine x, sine, and then cosine. And if you notice, it kind of follows the same pattern as we did above. This times this minus that times that is just exactly this. And this is negative 1 squared, which is 1. So this also equals 1. Okay, so negative 1 to the 3 minus 2 power. Okay, so now we take out the middle column, so 1, 0, sine and cosine. So this one, unfortunately, we do have a trig identity because we get 0 here, so it's just going to be cosine. And because is 1, it's going to be negative cosine. Okay. And now 3. So this goes away. So this gives me positive 1, and then this gives me negative sine x, because it gives me 0. So we got our 3 Dvorskys. Now we can solve for our 3 v's. And these ones are actually much easier than the last one, even though this looks like a horrendous mess. So the integral of, well, let's see, right, this is going to be our g of x. All that's going to be our g of x. Okay. Times w1, which is 1, so it just doesn't have anything, all over 1, because that's our Dvorsky. So now we're just taking the integral of this, which is great because this is already a property. This is secant x. Good. Same thing. W2 is negative cosine. Okay, so the best part about this is these end up canceling because we're multiplying, right? So this ends up being negative integral of tan. Integral of tangent is secant squared. So there's our V1. This is our V2. And then lastly, we do V3. And this time it's minus sine. Now, just like the other one, I'm going to put these together. Well, we have sine here. Secant is 1 over cosine, so sine over cosine is another tangent. So this ends up simply just tangent squared. x dx. So if you want, you could just integrate this yourself, or you could just find out the integral. It's just a u sub if you want to call that. You just convert it to sine and cosine, let u equal cosine, and do the whole process. Or you could just memorize this process. It's just equal to negative tan x plus x. That is V3. So now that we have that, we can finally write down our general solution. So first we have our three fundamental solutions. So C1 times 1 is just going to be C1. And the rest is just C2 with the cosine and sine. Okay. And now plus, and we'll go from here. So first is 1. That's y1, right? 1 times this, so it's just going to be itself. Okay, next is v2 times y2, so the negative secant. I won't simplify, just write it like that. It's already kind of messy just to do so. But one of the secants and cosines will cancel, but you get the picture. And then the last one, it'd be this times y3, so sine times this.